Dear friends, today we are discuss about NDT techniques. My name is Dr. N. Sri Rangarajulu, Assistant Professor, Department of Production Technology, MIT Campus, Anna University, Chennai. There are 6 basic types of NDT techniques. One is visual inspection, another one is a dye penetrant test, third one is magnetic particle testing, and some other techniques also radiography testing, and then this is ultrasonic testing. So one by one we will discuss about their applications and advantages, limitations, and all those things. So definition for NDT testing. Non-destructive testing is a testing of materials for surface or internal flaws or metallurgical condition without interfering in any way with the integrity of material or its suitability for service. NDT is the technology of assessing the soundness and acceptability of an actual component without affecting the functional properties of the component. The technique can be applied on a sampling basis for individual investigation or may be used for 100% checking of material in a production quality control system. So non-destructive testing is used for condition assessment and quality control in a wide range of industries, which include the applications, mining industry, automotive industry, oil and gas industry, medical devices, aerospace, maritime, military and defense application, power generation, manufacturing, packaging, waste management, and so on. Without destroying the material, we can able to find out the defects and other things. So destructive testing versus non-destructive testing, material testing, destructive testing, and non-destructive testing. Definition for destructive testing: measure accurate or specific characteristics of material by destroying the specimen. In non-destructive testing, monitoring or assessing material quality without destroying the component. In destructive testing, these testing techniques cannot be used for 100% inspection. Non-destructive testing, these testing techniques can be used for 100% inspection. Purpose of destructive testing: to find the ultimate tensile compressive strength, percentage of elongation, fatigue, creep strength, ductility, toughness, Young's modulus, etc. In non-destructive testing, to assess the surface, internal defects, coating, plating thickness, thickness measurement, structural assembly evolution, etc. Example for destructive testing: tensile testing, compressive testing, impact testing, fatigue testing, creep testing, bend testing, chemical testing, etc. Non-destructive testing: visual testing, liquid penetrant testing, magnetic particle testing, eddy current testing, ultrasonic testing, radiographic testing, acoustic emission testing, so on. So today we are discuss about only for non-destructive testing methods and their applications and their advantages and limitations. So most commonly used NDT techniques, the number of NDT methods that can be used to inspect components and make measurements in large or continuous to grow. Researchers continue to find new ways of applying physics and other scientific disciplines to develop better NDT methods. There are 6 NDT methods that are used most often. These methods are as follows: visual and optical testing, VT; magnetic particle testing, MT; penetrant testing, PT; eddy current testing, ET; ultrasonic current testing, UT; radiographic testing, RT. Like that, we can able to 6 basic NDT methods are there. Visual and optical inspection, or VT. Visual inspection or testing of almost all casting is carried out to detect the defects on the surfaces of the castings. Visual inspection may be carried out with naked eye or using a magnifying glass. Defects which are easily located by visual inspection are surface defects, tears, open blowholes, metal penetration, shift, surface roughness, swells, open shrinkage cavities, misrun, etc. Visual inspection is the simplest, fastest, and most commonly employed, but it needs greater skill on the part of the inspector to locate and identify different casting defects. Magnetic particle testing method This method is suitable for the detecting the surface and near surface discontinuous in magnetic materials, mainly ferritic steel and iron. Only for ferrous materials we can able to identify. MT uses magnetic fields and small magnetic particles, ion fillings, to detect the flaws in components. This NDT method is accomplished by inducing a magnetic field in a ferromagnetic material and then dusting the surface with ion particles of range of 20 to 30 micron, either dry or suspended in a liquid. Surface and near surface imperfection distort the magnetic field and concentrate ion particles near the imperfection, previewing a visual indication of the flaw. Magnetic particle testing, here they will have a crack and other things are there. Flux leakage will be provided. Here they will have a magnetic particle, ion particle cluster will form. Based on that, we can able to find out the cracks and other things. Principles of magnetic particle testing. The first step in magnetic particle testing is to magnetize the component that is to be inspected. If any defect on or near the surface are present, the defects will be create a leakage field. After the component has been magnetized, ion particles either in a dry or wet suspended form are applied to the surface of the magnetized part. The particles will be attracted and clustered at the flux leakage fields, thus forming a visible indication that the inspector can detect. Magnetic field orientation and flaw detectability. The property inspect a component for cracks or other defects. It is important to understand that the orientation between the magnetic lines of force and the flaw is very important. There are two general types of magnetic fields that can be established within a component. Type of magnetic fields: longitudinal magnetic field and a circular magnetic field. Here they will have a circular, here they will have a longitudinal. So magnetize the part in two directions is important because the best detection of defects occur when the lines of magnetic force are established at right angles to the longest dimension of the defect. As can be seen in the image below, if the magnetic field is parallel to the defects, the field will see little disturbance and no flux leakage field will be produced. Here they will have a flux leakage, and based on that we can able to find out the defects. These are all the some of the defects. And since defects may occur in various and unknown directions, each part is normally magnetized in two directions at the right angles to each other. The component below is considered. It is known that passing current through the part from end to end will establish a circular magnetic field that will be 90 degrees to the direction of the current. Therefore, defects that have significant dimension in the direction of the current, longitudinal defects, should be detectable. Alternatively, transverse type defects will not be detectable with the circular magnetization. So here they will have a circular magnetization. So here current will pass, crack at 45 degree will show the things, longitudinal crack will show. This is the magnetic field. Irregular cracks may show. This is the current field. Traverse crack will not show. Traverse crack will not show because of circular magnetization would be taking place. And then the particle that can be red or black oxide, or they can be coated with a substance with fluorescence brilliantly under ultraviolet illumination, black light. Particles start out as a tiny milled, a machining process, pieces of iron or iron oxide. The pigment, somewhat like paint, is bonded to the surfaces to give the particles color. Particles are available in a dry mix or a wet solution. Magnetic particles are suspended in a wet suspension such as water or oil. The magnetic particles inspection. The magnetic particles can either be applied to the component while the magnetizing force is applied or after it has been stopped. So method of generating magnetic flux in the test pieces, the application of permanent magnet to the surface, but this method cannot be controlled accurately because of indifferent surface cannot and deterioration in magnetic strength. Modern equipments generate the magnetic field electrically either directly or indirectly. In a direct method, high amperage current is passed through the subject and magnetic flux is generated at right angles to the current flow. In the indirect method, high amperage current is passed through a coil that encircles the subject. Here they will have a circular flux magnetic current magnetizing the current. Here they will have a longitudinal current. It can able to pass through this one. Based on that, we can able to find out the defects and other things. So magnetic particle inspection, there are advantages. Some of the advantages: simplicity of operation and application, quantitative, can be automated apart from DV. Disadvantages: restricted to ferromagnetic material, restricted to surface or near surface flaws, not fail safe in that lack of indication could mean no defects or process not carried out properly. So these are all the example for fluorescent with magnetic particle indication. Here magnetic particle wet fluorescent indication of the crack in drive shaft, and then magnetic particle wet fluorescent indication of the crack in the bearing. Here they will have a crack, and then magnetic particle wet fluorescent indication of the crack in the crane hook. Here they will have a small crack will be formed. Magnetic particle wet fluorescent indication of a crack at a sharp radius. Here they will have a sharp radius. They will have a defects like this. The third one is a penetrant testing method. This method is frequently used for the detection of surface breaking flaws in non-ferromagnetic materials, but it can also be used for ferrous material. This is penetrant testing method, non-ferrous metal and ferrous metals, both materials we can able to use it. The liquid penetrant inspection is a method that is used to reveal surface breaking flaws by bleed out of a colored or fluorescent dye from the flaw. This technique is based on the ability of a liquid to be drawn into a clean surface breaking flaw by action. The advantage that liquid penetrant testing LPT offers over an unaided visual inspection is that it makes defects easier to see for the inspector. So basic process steps of a penetrant testing: surface preparation, one of the most critical steps. The surface must be free of oil, grease, water, or other contaminants that may prevent penetrant from entering flaws. The simple sample may also require etching if mechanical operation such as machining, sanding, or grid blasting have been performed. Penetrant applications: once the surface has been thoroughly cleaned and dried, the penetrant material is applied by spraying, brushing, or immersing the part in the penetrant bath. Penetrant dwell time is the total time that the penetrant is in contact with the part surface. Capillary action draws the penetrant into the crack during the period. That may be, dwell time may be 10 seconds minimum. And then excess penetrant removal. The surplus penetrant on the surface is then removed completely. Depending on the penetrant system used, this step may involve cleaning with a solvent, direct rinsing with water, or first treating the part with an emulsifier and then rinsing with water. Developer application: a thin layer of developer is then applied to the sample to draw penetrant trapped in the flaws back to the surface where it will be visible. Developers come in a variety of forms that may be applied by dusting, dry powder, dipping, or spraying wet developers. Indication development: the developer is allowed to stand on the part surface for a period of time sufficient to permit the extraction of the trapped penetrant out of any surface flaws. This development time is usually minimum of 10 minutes. Inspection is then performed under the appropriate lighting to detect indication from any flaw which may be present. Clean surface. The final step in the process is to thoroughly clean the part surface to remove the developer from the parts that were found to be acceptable. This is the steps in liquid penetrant testing. Penetrant is applied to the surface and enters defects. Here the penetrant will enter black or red or whatever color it can able to available. We can apply the penetrant. This is a red color penetrant applied to with the help of a brush or spray, and then excess penetrant removed from the surface with the help of cloth and something we can able to remove the excess penetrant, and we can able to third step developer is used for spray or apply and then cleaned thoroughly. Accentured indication of crack as penetrant spread around the opening. Here they will have a penetrant will enter here, so it can able to find out the cracks and other things. Next, basic processing steps of your penetrant testing. Penetrant material. Today's penetrants are carefully formulated to produce the level of sensitivity desired by the inspector. To perform well, a penetrant must spread easily over the surface of the material, drawn into surface breaking defects by capillary action, remain in a defect but remove easily from the surface of the part, remain fluid so it can be drawn back to the surface of the part through the drying and developing steps, highly visible or fluorescent brightly to produce easy to see indications, not harmful to the material being tested or the inspector. So these are all the important properties of penetrant. The penetrant materials come into two basic types. These types are listed below. Fluorescent penetrants. Fluorescent penetrants contain a dye or several dyes that fluorescence when exposed to ultraviolet radiation. Visible penetrants. Visible penetrants contain a red dye that provides high contrast against the white developer background. The emulsifier, when the removal of the penetrant from the defect due to overwashing of a part is a concern, a post-emulsifiable penetrant system can be used. Post-emulsifiable penetrants require a separate emulsifier to break the penetrant down and make it water washable. Developers, the role of a developer is to pull the trapped penetrant material out of the defects and spread it out on the surface of the part so it can be seen by an inspector. The fine developer particles both reflect and refract the incident ultraviolet light, allowing more of it to interact with the penetrant, causing more efficient fluorescence. Developers' perform is to create a white background, so there is a greater degree of contrast between the indication and the surrounding background. Basic processing steps of a penetrant testing. 6 standard form are dry powder, water soluble, water suspendable, nanoqueous. Type 1 is a fluorescent, solvent based nanoqueous. Type 2 visible dye, solvent based and special forms. Advantages: the method has highly sensitivity to small surface discontinuous. The method has no material limitations. Large areas of large volumes of parts, materials can be inspected rapidly and at low cost. Parts with complex geometric shapes are routinely inspected. Indications are produced directly on the surface of the part and constitute to visual representation of the flaw. Penetrant materials and associated equipments are relatively inexpensive. Some disadvantages also there in dye penetrant testing. So only surface breaking defects can be detected. Only materials with relatively non-porous surfaces can be inspected. Pre-cleaning is critical since contamination can mask defects. The inspector must have direct access to the surface being inspected. Surface finish and roughness can affect inspection sensitivity. Post cleaning of acceptable parts of material is required. Chemical handling and proper disposal is required. So these are all the examples of liquid penetrant test investigation. Here they will have a cracks and other things. Here also the crack will be identified. Fourth one is eddy current testing. So eddy current inspection is one of several NDT methods that use the principle of electromagnetism as the basis of conducting examination. Electrical currents are generated in a conductive material by an induced alternating magnetic field. The electrical currents are called eddy currents because they flow in circles at and just below the surface of the material. Interruptions in a flow of eddy currents caused by imperfection, dimensional changes, or changes in the material conductive and permeability properties can be detected with the proper equipment. Since eddy currents tends to concentrate at the surface of the material, they can only be used to detect the surface and near surface defects. So these are all the basic principles. Step 1, step 2, step 3, step 4, flux is magnetic flux is induced, and find out the defects in the 6th step. So eddy currents can be produced in any electrically conducting material that is subjected to an alternating magnetic field, typically 10 Hz to 10 megahertz. The alternating magnetic field is normally generated by passing an alternating current through a coil. The magnitude of the eddy currents generated in the product is dependent on the conductivity, permeability, and the setup geometry. Any change in the material or geometry can be detected by the excitation coil is a change in the coil impedance. The simplest coil comprises a ferrite rod with several turns of wire wound at one end and which is positioned close to the surface of the product to be tested. So here ferro eddy current testing, this is no crack circular pattern. Here they will have a surface crack, distorted circle. Here they will have a crack will be identified. So detected eddy current signals contain amplitude and phase information and which can be displayed on the CRT type displays, non-digital displays. The depth to which the eddy current penetrant a material can be changed by adjusting the test frequency. The higher the frequency, the lower the penetration. The surface testing for cracks in single or complex shaped components, coils with a single ferrite core winding are normally used. The eddy current test is purely electrical. The coil units do not need to contact the product surface and thus the technique can be easily automated. The systematic illustration of eddy current testing of the drawn tube for a longitudinal defects. Here they will have a longitudinal defect. So we can able to detect the coil and the excitation of the coil. So based on that, we can able to find out the eddy current test. With the help of eddy current test, we can able to find out the longitudinal defect. Advantages of eddy current test: suitable for determination of wide range of conditions of conducting materials such as defect detection, composition, hardness, conductivity, permeability, etc. in a wide variety of engineering materials. Inspection gives immediate results. Defect detects surfaces and near surface defects. Equipment is very portable. Minimum part preparation is required. Test probe does not need to contact the part. Inspect complex shapes and sizes of conductive materials, suitable for total automation. So disadvantages: the wide range of parameters which affect the eddy current responses means that the signal from a desired material characteristics, example, a crack, can be masked by an unwanted parameter, example, hardness change. Only conductive materials can be inspected. Non-conductive material we cannot able to inspect. Skill and training required is more expensive than other techniques. Careful selection of probe and electronic will be needed in some applications. Depth of penetration is limited. Flaws such as delaminations that lie parallel to the probe coil winding and the probe scan direction are undetectable. So ultrasonic testing. Fifth one is ultrasonic testing. Ultrasonic testing use transmission of high frequency sound waves into a material to detect imperfections or to locate changes in material properties. This technique is used for a detection of internal and surface, particularly distant surface, defects in sound conducting materials like ferrous and non-ferrous metallic objects, as well as is in plastic and ceramics. All the materials we can able to make with the help of this ultrasonic testing, ferrous, non-ferrous, plastics and ceramics. The most commonly used ultrasonic testing technique is pulse echo, wherein sound is introduced into a test object and the reflection echoes are returned to a receiver from internal imperfections or from the parts geometrical surfaces. So ultrasonic testing, the typical ultrasonic testing inspection system consists of several functional units such as the pulsar or receiver, transducer, and display devices. The surface of casting to be inspected by ultrasonic is fairly smooth by machining. A couplant is provided between the transducer and the casting surface. The couplant is material, usually liquid, that facilitates the transmission of ultrasonic energy from the transducer into the test specimen. A pulsar or receiver is an electronic device that can produce high voltage electrical pulses. Driven by the pulsar, the transducer, a piezoelectric crystal, generates high frequency 1 megahertz to 6 megahertz ultrasonic energy. The sound energy is introduced and propagates through the material in the form of waves. When there is a discontinuity, such as crack in the wave path, part of the energy will be reflected back from the flaw surface. The reflected wave signal is transformed into an electrical signal by the transducer and is displayed on a screen. The reflected signal strength is displayed versus the time from signal generation to when the echo was received. Signal travel time can be directly related to the distance that the signal traveled. From the signal, information about the reflector location, size, orientation, and other features can be gained. So here they will have a principles of ultrasonic testing, pulsar and receiver, transducer. In between, we can able to apply a couplant. This is the workpiece. This is the echo system. Based on the crack, we can able to find out the echo. Crack echo. Here they will have a smaller echo. So based on that, we can able to find out the defects in the where it can able to defect will occur and all those things. Not only this ultrasonic testing, we are able to find out the cracks and we can able to find out the thickness of material thickness also. Piezoelectric transducers, the conversion of electrical pulses or mechanical vibration and the conversion of returned mechanical vibration back into electrical energy is the basis for ultrasonic testing. The active element is the heart of the transducer as it converts the electrical energy to acoustic energy and vice versa. The active element is basically a piece of polarized material, that is some parts of the molecule are positively charged while other parts of the molecules are negatively charged with the electrodes attached to the two of its opposite faces. The piezoelectric crystals made from quartz crystals materials were primarily used. The active element of most acoustic transducers used today is piezoelectric ceramic, which can be cut in various ways to produce different wave modes. The thickness of the active element is determined by the desired frequency of the transducer. A thin wafer element vibrates with a wavelength that is twice its thickness. The higher the frequency of the transducer, the thinner the active element. This is the piezoelectric transducer. Here they will have a casing, epoxy potting, backing material, the electrodes, piezoelectric elements, wear plates, and ground wire, signal wire, coaxial cable connector. Here they will have backing, active elements, magnetic energy, and wave in phases and all those things. Based on that, we can able to find out the defect. What is the ultrasonic testing couplant? The couplant is material, usually liquid, that facilitate the transmission of ultrasonic energy from the transducer into the test specimen. Couplant is generally necessary because of the acoustic impedance mismatch between air and the solids, such as the test specimen is large. The contact ultrasonic testing, a thin film of oil, glycerin, or water is generally used between the transducer and the test surface. When the scanning over the part or making precious measurement, and impression technique is often used. This is a contact ultrasonic testing. This is immersion techniques. Contact testing, here they will have a couplant and a test specimen and transducer. And here they will have a search unit and water is a couplant, immersion technique. Here they will have a workpiece. Based on that, we can able to find out the defects and other things. So pulsar receiver, the pulsar section of a instrument generates short, large amplitude electric pulses of controlled energy. Most pulsar sections have very low impedance. Outputs of better drive transducers. In the receiver section, the voltage signal produced by the transducer, which represent the received ultrasonic pulses, are amplified. The amplified radio frequency signals is available as an output for display or capture for a signal processing. Advantages: it is sensitive to both surfaces and subsurfaces discontinuous. The depth of penetration for flaw detection or measurement is superior to other NDT methods. Extremely sensitive if required. Portable. It is highly accurate in determining reflector position and estimating size and shape. Minimal part preparation is required. Electronic equipment provide instantaneous results. Detailed images can be produced with the automated system. It has other uses such as thickness measurement in addition to flaw detection. Ultrasonic testing method, same principle. We can able to find the measurement of the thickness also possible. Flaw detection also possible. So disadvantages: surface must be accessible to transmit ultrasound. Skill and training is more extensive than with some other methods. It normally requires a coupling medium to promote the transducer of sound energy into the test specimen. Materials that are rough, irregular in shape, very small, exceptionally thin, or not homogeneous, are difficult to inspect. Cast iron and other coarse-grained materials are difficult to inspect due to the low sound transmission and high signal noise. Linear defects oriented parallel to the sound wave may go undetected. This technique is suitable for the detection of internal defects in ferrous and non-ferrous metals and other materials also. Radiography involves the use of penetrating gamma or X-ray radiation to examine parts and products for imperfections. An X-ray generator or radioactive isotope is used as a source of radiation. The X-rays and gamma rays are electromagnetic radiation of exactly the same nature as light, but of much shorter wavelength. Wavelength of visible light is on the order of 6,000 Armstrong, while the wavelength of X-rays is in the range of 1 Armstrong, and that the gamma rays is 0.001 Armstrong. This very short wavelength is what gives X-rays and gamma rays their power to penetrate material that light cannot. The X-rays and the gamma rays are absorbed by the material through which is passes. The greater the thickness, the greater the absorption. Furthermore, the denser the material, the greater the absorption. X-ray and gamma rays also have the property light of partially converting silver halide crystals in the photographic film to metallic silver in the proportions to the intensity of the radiation reaching the film and therefore forming a latent image. This can be developed and fixed in a similar way to normal photographic film. Material which internal voids is tested by placing the subject between the source of radiation and the film. The voids show as darkened areas where more radiation has reached the film on a cleaner background. This is the principle of radiographic testing. The source of radiation, sample, defects, film package here. The processed film is here. So based on that, the X-rays are produced by an X-ray generator, and gamma radiation is the product of radioactive atoms. Due to their short wavelength, they have more energy to pass through matter. As they pass through a matter, they are scattered and absorbed, and the degree of penetration depends on the kind of matter and the energy of the rays. There are two different atomic processes that can produce X-ray photons. One is breaking radiation, other is called K-shell emission. They can both occur in the heavy atoms of tungsten. Tungsten is often the material chosen for the target or anode of the X-ray tube. The gamma radiation is one of the three types of neutral radioactivity. Gamma radiation is the product of radioactive atoms depending upon the ratio of neutrons to protons within its nucleus. An isotope of a particular element may be suitable or unsuitable. When an atom undergoes radioactive decay, it emits one or more forms of radiation with sufficient energy. When the X-rays or gamma rays are directed into an object, some of the photons interact with the particles of matter, and their energy can be absorbed or scattered. This absorption and scattering is called attenuation. The number of photons transmitted through a material depends on the thickness, density, and atomic number of the material and the energy of the individual photons. This is the attenuation of X-ray with the distance travel in the material. This is the attenuation of X-rays. So radiographic film, X-ray films for general radiography consist of an emulsion gelatin containing radiation sensitive silver halide crystals such as silver bromide or silver chloride and a flexible transparent blue tinted base. When X-rays, gamma rays or light strike the grains of the sensitive silver halide in the emulsion, some of the bromide ions are liberated and captured by the silver ions. This changes is of such a small nature that it cannot be detected by ordinary physical methods and is called latent image or hidden image. However, the exposed grains are now more sensitive to the reduction process when exposed to a chemical solution developer, and the reaction results in the formation of black metallic silver. Image considerations. Radiographic sensitivity is a measure of quality of an image in terms of the smallest detail or discontinuity that may be detected. The factors affecting radiographic image quality, radiographic image quality, contrast and definitions, contrast subject features, absorption differences in the subject, wavelength of the primary radiation, secondary radiation from scattered. Film factors, type of the film, grain size, chemistry of the film processing chemicals, concentration of film processing chemicals, development time, amount of film agitation, overall film density. Definition for geometric factors: size of the source, focal spot size, source to film distance, specimen to detector film distance, the observedness of specimen thickness changes, movement of the specimen during the exposure. Film factors: type of film, grain size, moting due to user of a fluorescent screen, wavelength of the primary radiation, development time, other film processing factors. So radiographic interpretation of the casting defects, gas porosity of the blowholes. Here they will have a gas porosity, sand inclusion and dross. Here they will have a sand inclusion defects, shrinkage cavity. Here they will have a shrinkage cavity, and the cracks. Here there are some cracks and other things. Here there are having a inclusions. So these are all the defects. With the help of radiographic interpretation, we can able to find out the casting defects. And advanced technique of radiographic testing, computed tomography. Computed tomography, CT, is a powerful non-destructive evaluation, that is a NDE technique for producing 2D and 3D cross-sectional images of an object from flat X-ray images. So this is the computed tomography. This is a X-ray tube, X-ray beam, test component, and image intensifier, analog video signal, computer-controlled turntable, and here they will have a serial linkage, turntable interface unit, and a PC with image capturing hardware. This is the computer tomography setups. Here they will have a specimen will be kept and rotated in the table, and we can able to find out the defects. So this test component is placed on a turntable stage, that is between a radiation source and an imaging system. The turntable and the imaging system are connected to a computer so that X-ray images collected can be correlated to the position of the test component. The imaging system produces a two-dimensional pseudograph image of the specimen, just like a film radiograph. Specialized computer software makes it possible to produce cross-sectional images of the test component as if it was being sliced. So advantages: information is presented pictorially, a permanent record is provided which may be viewed at a time and place distant from the test, useful for thin sections, sensitivity declared on each film, suitable for any material, ferrous, non-ferrous, ceramic, plastic, whatever it may be. And the disadvantages: generally an inability to cope with thick section, possible health hazard, need to direct the beam accurately for two-dimensional defects. The film processing and viewing facilities are necessary, is an exposure compound, not suitable for automation unless the system incorporates fluoroscopy with an image intensifier or other electronic aids, not suitable for surface defects, no indication of depth of defects below the surface. So, dear friends, today we are discuss about NDT techniques. Whatever NDT techniques, we are able to find out the defects in casting and weldments and all those things. We can able to discuss about the dye penetrant test and ultrasonic testing and magnetic particle testing and radiography testing and so on. So any doubts, any clarifications, you can able to make put a questionnaire or comment in the comment box. Based on that, I can answer the your questions, and you can able to support me for the future videos. And this may be very useful for NDT for welding and the casting students. So it may be very useful for your career and all those things. Thank you very much for your patient listening. Thank you.